Hi team, Distance Learning Day 2. Today we're going to continue our look at different types of inequalities with rational inequalities. If you remember, in our last video we looked at polynomial inequalities. A polynomial is a sum of monomials. Today we're going to look at rational inequalities. Remember that a rational function is a ratio of two polynomials. So we're going to have a fraction with a polynomial in both the numerator and the denominator. So, looking at our objective, today we're going to solve rational inequalities algebraically and graphically. We're going to jump right into this since we did a lot of the talking in the last video. And we're going to try and solve this rational inequality. We've got the ratio x minus 1 over x squared minus 4 is greater than or equal to 0. And we're going to do it by graphing the function r of x that you see here. Notice we have the same rational expression, right? The same ratio of polynomials. So we've spent quite a bit of time already graphing rational functions. I'm not going to review each individual step, but I will remind you that these are all things that we can find as we look at the graph of this rational function. To find our x-intercept, we're going to set r of x equal to 0. We'll solve for x. We get the ordered pair 1, 0. To get the y-intercept, we will evaluate r of x at 0, and r of 0 is 1/4. So we have our y-intercept at the ordered pair 0, 1/4. This is already in lowest terms, so we can find the vertical asymptotes by looking at the real zeros of the denominator. I have factored x squared minus 4 into the conjugates x plus 2 and x minus 2. So we have vertical asymptotes at x equals negative 2 and x equals positive 2. And then the horizontal asymptote is determined by the end behavior of our rational function. If we look at this, the degree of the numerator is 1 and the degree of the denominator is 2. So the end behavior of this function is like the end behavior of 1 over x. And as x approaches positive or negative infinity, 1 over x approaches 0. So our horizontal asymptote is that horizontal line y equals 0. Okay. Taking all these pieces of information and putting them on the graph, we end up with this graph. You can see all of the intercepts and asymptotes are clearly labeled. I labeled my intercepts as points A and B. You can see them up here. And my asymptotes I always remember to label as equations. When you look at my graph, the next thing you'll see is that I have already highlighted part of my graph green. If we return our attention to the original inequality, we want this rational expression to be greater than or equal to 0. This function is greater than 0 for all points that are above the origin. So I've highlighted the portions of this graph that are above the origin. Okay. Our solution set then are all of the x values that we have highlighted. So if we look at our solution set to this inequality, we have the half open interval from negative 2 to 1. Let's talk about why we're closed at 1 really quick. If you'll remember, our x-intercept up here, point A, was 1, 0. And because our original inequality said that we could be greater than or equal to 0, 1 is the value of x that makes this rational function equal 0. Therefore, it's included in the solution set. Our solution set contains a union with the second interval, the open interval 2 to infinity. That's this portion of the curve here. This is obviously going to be an open interval. 2 is not in our domain. It's the value of the vertical asymptote. And infinity, of course, is not a value that we can equal. Take a moment, pause this video, and make sure that you understand all there is about solving this rational inequality graphically. All right, the second portion of what we're going to do is we're going to work to solve a rational inequality algebraically. You'll remember that when we did this with polynomial inequalities, we introduced the idea of critical values. Okay? Today we're going to look at the critical values of a rational function. This is a definition you'll want to be certain that you understand. So go ahead again, pause the video. Critical values of a rational function are the real zeros of the polynomials in the numerator and the denominator. So our rational function is a ratio composed of two polynomials. The critical values are the real zeros of both of those polynomials, the numerator and the denominator. Let's take a look at an example. This is the last example we'll do today, and then we'll give you a chance to solve some rational inequalities. So we're going to look at solving the rational inequality 3x squared plus 13x plus 9 over the quantity x plus 2 squared is less than or equal to 3. Now, it's going to be very tempting when you see this to multiply both sides of the inequality by the denominator of the left in order to get rid of the fraction. You do not want to do this. Okay? If we take our mind back to our definition of critical values of a rational function, we know we need to explore the real zeros of the numerator and the denominator. So we need to maintain that denominator. That's going to be something that through practice you kind of build that memory, and you know that in this case you want to keep both the numerator and the denominator. So instead of doing this work to clear the fraction, instead what we're going to do is we are going to compare our rational expression to 0. And I don't want to work this problem less than or equal to 3. I want to work it less than or equal to 0. Okay? So what I've done, I've subtracted 3 from both sides of the inequality. That's a simple step. Now to subtract these fractions on the left, if I want to do this fraction subtract this fraction, I'm going to need a common denominator. So my common denominator is that quantity of x plus 2 squared. Take a look at that work for the common denominator. When I subtract two fractions that have a common denominator, I keep the denominator and I subtract the numerators. Now I've left each numerator in a quantity using my parentheses, but you can notice that I have simplified this numerator by following the order of operations. After distributing the negative sign and combining like terms, this entire rational expression simplifies to what you see here. So this is actually the expression that we are going to use when we solve our inequality. We're going to solve the inequality x minus 3 over the quantity x plus 2 squared is less than or equal to 0. Go ahead and pause the video for a minute and catch your notes up to where we are. After you've done that, we'll start solving this inequality using critical values. Okay, remember our definition of the critical values of a rational function are the real zeros of both the numerator and the denominator. So I've clearly labeled my work to make it easy to follow what I've done here. This is my work for finding critical values. I've labeled that working in the numerator, the only critical value is x equals 3. Working in the denominator, I have the critical value x equals negative 2, and I've made a note that this has a multiplicity of 2. I know that because the factor had an exponent of 2. Therefore, my critical values are 3 and negative 2. Next thing we'll do is we'll graph our critical values on a number line. You guys are used to that by now from working with polynomials. You can see that at negative 2 I've got an open point. Negative 2 was a real zero of the denominator and it's not in the domain. At the critical value 3, I have a closed point. Because 3 is in the domain, 3 is a critical value of the numerator, and it makes my fraction equal to 0. All the way back up here, we can see that we're solving for when this expression is less than or equal to 0. So including 3 gives us the equal to 0. Just as with polynomials, I have divided my number line into 3 intervals using my critical values. I've selected an arbitrary test value within each interval. It doesn't matter if you choose the same values as I have or not, as long as the value you choose is within the interval you're testing. After testing my function at each of these, I've concluded that at the first two intervals, my test values create negative function values. But my test value in the third interval created a positive function value. Since we wanted to be less than or equal to 0, I've used both of these intervals as my solution set. Notice again in my solution set that I am closed at the value 3. So I have the solution set negative infinity to negative 2, an open interval, union negative 2 to 3, where I'm open at negative 2 because it's a critical value of the denominator, but I'm closed at 3. One last thing about this before I leave you to practice on your own. Notice that when we had the multiplicity of 2 with our critical value in the denominator, that our behavior of our function was the same on each side of that critical value. That makes sense based on our knowledge of vertical asymptotes and the graphic behavior on either side of that asymptote. I hope this video helped you to understand how we solve rational inequalities graphically and algebraically. Now we'll give you a chance to practice some on your own. Thanks for listening. Stay healthy.